In this video, we're going to see how to use the regression function in Excel, and we're going to apply this to some data looking at local education agencies, so individual school systems, and the amount of federal funds that are applied for child nutrition on a per pupil basis. So this is child nutrition per pupil expenditures federal. And we're also going to look at how that's related to the percentage of free and reduced meals served in each of these school systems. So first, just looking at a scatter plot, we can see that there is a relationship. We might also do a correlation analysis for this as well, but we can see that in general, as the percentage of free and reduced meals increase, we're going to see and expect a higher level of per pupil expenditures from the federal government. So to run a simple linear regression, so this is assuming, again, that the relationship is linear, and we can see that in the scatter plot. Doesn't look like there's another shape that would better describe this than a linear relationship. So in the data ribbon in Excel, if you go to data analysis, select the regression option. For our input Y range in Excel, this is what we're trying to explain. We want to explain the child nutrition per pupil expenditures from the federal government. So we're going to select our data in column D. For our input X range, we're using percentage free and reduced meals to help predict our per pupil expenditures. So we're going to select that as our input X range. We have labels. I selected row 1. Those are where our labels are, so we want to make sure we have that checked. And we can put our output on a new worksheet. You can also select information to see specifics about the residuals, including the plots, and a normal probability plot as well. So if you'd like to see those details, you can select those options as well. So we'll see our summary output on a new worksheet. Some of the information is cut off, so usually I adjust the column widths so we can see everything. And I'll highlight some of these key information that are provided. The multiple R, this is the correlation coefficient between the observed and the predicted values. Ranges from 0 to 1, and a small value indicates little or no linear relationship between the dependent and independent variables. R square, this is a common statistical measure when we're looking at regression, and it shows us how close the data are to the fitted regression line. This is also known as the coefficient of determination, so you might hear that term as well. And the basic definition is that it's the percentage of the response variable variation that's explained by the linear model that is created here. So the R squared is the explained variation divided by the total variation. It's always between 0 and 100. 0 indicates that the model explains none of the variability of the response data around its mean, and 100% indicates that the model explains all of the variability of the response data around its mean. The adjusted R squared is similar to R squared. It just accounts for having multiple predictors. So if you have a larger number of predictors that doesn't improve your model, you're going to see the adjusted R squared go down. So this is mostly useful if you're looking at comparing multiple models and adjusting for the number of regressors that you're using. We're also provided with the number of observations, the ANOVA table that is testing for whether or not our coefficients are likely or are equal to 0. That's our null hypothesis. The alternative hypothesis is that the coefficient, in this case the percentage of free and reduced meals, is not equal to 0. So we see a highly significant F test here. This is a very small value, so we can conclude that at least, in this case, since we only have one variable, at least one of our regressors is not, the coefficient is not equal to 0. And then in our last segment here we have the coefficients. So these are the least square estimate of the coefficients, the associated standard error, the t-statistic, the associated p-value. And so for the intercept and for, in particular, our coefficient with our percentage of free and reduced meals. It's a very small p-value, so we can conclude that there's not statistical evidence that the coefficient is equal to 0, which supports the alternative hypothesis that the coefficient is much different from 0. And we can use this information to actually generate our equation that explains the relationship between federal child nutrition per pupil expenditures and the percentage of free and reduced meals. So writing it in that terminologies, if we have per pupil expenditures for child nutrition, federal funds equals the intercept, so negative 118.92 plus 945.58 multiplied by the percentage of free and reduced meals. In this case, this percentage would actually need to be input in decimal form for a correct estimation. So if you're actually inputting something, so if we wanted to estimate what would we predict if we had 50% free and reduced meals, we would want to input 0.5 here, and we can actually do this calculation. And we would estimate that the federal government's per pupil expenditures in child nutrition for a school with 50% free and reduced meals is $353.87.